Okay, let's get started. So in the last lecture, we talked about how to use Raster IO to open raster data, get some basic information, and we also talk about some of the visualization techniques that you can use to plot a single band, or you can stack multiple bands together. And for this lecture, we're going to continue with that, but we're going to do a little bit more raster data manipulation. So it's very much similar to when you use desktop GIS. You open a raster data set, and then you're trying to extract some information, do some, in ArcGIS, it's called raster calculator, for example, right? You can do some mathematical operations on the raster data. For example, you can extract normalized difference vegetation index, water index, or you can try to calculate the minimum, the maximum values of every pixel across the entire image. So, and if you know how to use programming, it's a lot more flexible. So you are not limited to the functions they provide by the desktop GIS. You can write your custom function, and you can apply that function to each individual pixel. So in this lecture, we're going to go through some examples how we can actually, for example, calculate vegetation indexes, index, and how you can do a little bit more than that. For example, I give you a DM. You can extract elevations above, for example, 2,000 meter, 1,500, or you can even do some mathematical equations. You can subtract, you can minus, or I can give you 2DM. You can quickly calculate, for example, the digital elevation model minus the digital elevation model. You can get, for example, the building height, the tree height, or something like that. And it's very powerful because Raster built on top of NumPy array, and NumPy array has a lot of functionalities. So we can use that to do calculation. We can also, if we have time, we can later the semester, we can do some real world applications. We can use, for example, SciPy to do some machine learning, for example, scikit-learn, or you can use scikit-image to actually do a lot of image processing. So there are tons of things you can do, but I don't want to overwhelm you too much right now, but just that you know, it's a little bit tedious if you first learn how to use Raster IO to deal with image. Like why do I need to open? How do I get the basic information? And even more tricky is like when you're trying to write the result to a raster data, there's something that you need to pay attention to, because it's not just like in desktop GIS. You do some mathematical equation and then just right click and then just export, and everything just works fine. In programming, it's a little bit challenging for beginners. You need to figure out, okay, what kind of format you need to write, and what's the width and the height, and what's the data type. There's so many things you need to consider. But once you have a good understanding, you'll be very powerful and very flexible for you to handle any real world scenario. Again, so we talk about import the library, reading the data, accessing the metadata, and then just simple plotting of the raster data. And you can customize the color map. You can also plot vector data on top of the raster data. You can create a color bar. You can also do some simple manipulations. So in today's lecture, we're going to use this same sample data set, a Landsat data set, entire Landsat scene, but it's only 90 meter resolution. And then we're going to go to this section, basic band mass. So how do we calculate the vegetation index? For example, how do we extract the vegetation out of this imagery? Or how do we extract the water out of this Landsat imagery? So let me switch back to my VS Code here. So I'm going to go to the NDVI section in here. So if you're doing remote sensing, probably heard about the vegetation index. So it's a very simple equation that uses the near infrared band and also the red band. So the reason for that, because the spectrum of vegetation has high reflectance in the near infrared, but have relatively low reflectance on the red band. So this is usually we use to calculate the so-called normalized. The reason why it's called normalized is actually you are transform the value to a certain range. Usually it's maybe from 0 to 1. In this case, it's from -1 to 1. So if a high reflectance in the near infrared band, and for vegetation, high minus low divided by high plus low is going to be high value. Okay, but if it is opposite for other features, the red band is high, the near infrared band is low. So when you low minus high, it's going to be negative divided by the sum. So you become, the range will be from -1 to 1. So this is usually how we use this so-called normalized difference index. Basically, A minus B divided by A plus B. The range will become from -1 to 1. And this is how we can do that. So look at this one here, near infrared band. So earlier, for example, here we already read the band. So we know the near infrared band is from band 5. So this one here, band number 5 is a near infrared band. And the red band is a band 4. So we use this one. As I said, src.read. So when we open the data, again, let me come back to the beginning here just to highlight this one again. So this is the imagery that we're trying to open. And then once we open, you will have the src pointer pointing to the file. As I mentioned in the previous lecture, the src is just a pointer. It doesn't actually read the data. So you can just type src and then .read parentheses, okay? So if you don't provide anything, right now you're reading the entire data set. So this data set has 7 bands, right? So if you don't remember, you can always src.meta and then run it. So you will see here, this one, the count. That means it has count is 7. That means it has 7 bands. So if you're trying to read 7 bands all together, then you can just use src.read. So I can show you, for example, full data equal to src.read. Take a look at this one. And you will notice it's taking time because it's going to the internet to retrieve the file. So this is when it's really downloading the file to your computer. So it might take some time depending on how big is the file. If it's really big, this is going to take a couple minutes. So for this particular file, it's 119 megabytes. It's not super big, but still decent size. That's why it takes here 15 seconds to read the file. And once you have that, you can print it out, for example, full data, and then execute it. So you see here, these are a bunch basically the outside. If you go back to the imagery that I showed you above, anyway, it's just too much. So for example here, look at this one, right? You have the border, they're all black color. So that means those are no data, no data. There's no pixel values. And that's why in here you see this like negative INF, basically like negative infinity. This is basically the border, those black color. But inside there are real values in there. And the other way you can check is like, if you look at this one array, have 3 brackets in here. So this one is a 3-dimensional array. If you can check dot shape, where is it? Dot shape, you see here 7 and then 25, 63, 24, 85. So this one is 7 here at the beginning. So this is a 3-dimensional array. So you have 7 bands and then 2,563 rows and 2,485 columns. So that means, oh no, yeah, row and column. So band, row, and column. So this is what is being utilized by Raster IO. So in this case, we have 7 beings. So right now we have access to the entire data set, right? So one thing you can do here, right now we have the full data. We're using the read function, read all of them, but you can also provide an index, for example, src.read1. What does this mean? Which band are we reading? So what does band 1 mean here? Where's the table? Or is it up here? So keep it in mind, Raster IO, the index start from 1, not from 0. So don't be confused. If you put 0, it's not going to work. So that means we're reading band number 1. If you use read 1, so you can pick up the band you want to read. You don't have to load all the data. So if you are having imagery that has 100 bands, you probably don't want to read them all at once because it's taking time. So you can actually specify the band that you want. And this is what this example is about. If you scroll down to this NDVI, here, src.read5, so that means you are reading the near infrared band. And also we're reading the red band. We're also reading the green band. Although the green band here, we are not really using it right now. We are only using it for plotting. But this one is stacking all the 3 bands together. So you can think about you are selecting a subset of those 3 bands. You can do the same thing in here. For example, when we do the full data, this one here, you can also like do the indexing. I'm going to show you how to do the slicing. So you can get a subset, or you can get a small, not all the same bands, but if you just know 3 bands, similar to the list that we used in the past to do the indexing. We can do that again here. I will show you later. So let's take a look at this example now. So this one, just to show you quickly. So we are basically extracting the near infrared, the red and green bands, and then stack them together using this NumPy D stack. So basically you're putting those 3 bands together, and then, so this one here, this RGB, if you print out the shape, for example, RGB.shape, right? So you notice right now it actually changed. So for Matplotlib is XYZ. So it's switching the number. So right now the band is actually at the end. So 3 bands. So it's like not row. Let me see here. Yeah, row and column and channel. How many channels in there? It's different from the raster IO. The channel is at the beginning. Okay. Once we have the red and the near infrared band, and this is where you can write the simple calculation. This equation in here is to use to calculate the NDVI. And some of the values are incorrect, so there's some value greater than 1 is not supposed to be. Then we can use this clip function to clip them to -1 and 1. So basically any value less than -1 is going to change to be -1. Anything value greater than 1 is going to be changed to 1. So in that way, it's really normalized. And let's take a look at this one, right? So this is what it shows up. This is the normalized difference vegetation index. So you can see here, if the value is close to 1, it's going to be green color. If the value is close to -1, it will be red color. So you can clearly see here, right? Then we can use the NDVI to actually extract the vegetation. For example, if you want to extract vegetation from this data imagery, then we can say, okay, if the NDVI is greater than, let's say, 0.1, it's going to be vegetation. So you can clearly go back to the previous one here, right? If some of these like red color, those are usually the forest, right? So you can see the vegetation index is green color for this area. So again, take a look at this one, right? So the green color, so the water here is darker color. And this is how we do the calculation and also plot it out. And one thing you can do is to set a threshold. So in this case, we already have the NDVI. So the value ranges from -1 to 1. And if you want, you can actually do a selection, and you can do the filtering. So what I can do here is to create a new code block. And so this is the NDVI, right? NDVI right now is only just one NDVI.shape. You can take a look at the shape. You see right now it's without the channel. Without how many bands? Because it's just one single band. So if this is something you do, we can do for example, NDVI and then NDVI greater than 0.5. 0.5 probably is too much, maybe 0.1, okay? So you're going to end up with like one, just a single value. So this is going to get all the value from the array. But you can also calculate the maximum. For example, I can show you here. If you want to like have multispectral bands, and you want to calculate the maximum value of across all the bands, for every pixel location, we can also use NumPy to do that. So let me show you this example. You'll be np.max, for example. You try to calculate the max value for every pixel, and then using the 7 bands. So we can put in the full data here. If you're just doing this way, it will just give you one number. So look at this, full data np.max. So that means it's putting all the pixel values and then calculate the maximum value for every pixel. But this is probably not what we want. What we want is we want to generate an image that is the maximum for every location. So for this pixel, it's going to calculate the maximum for these 7 bands. Another pixel, 7 bands, get the maximum, get the maximum. So if you don't provide an axis, it's going to calculate, put them all together just as a one dimension. So there's an axis parameter here. Axis equal to 0. Equal to 0, that means right now, this full data, again, if you come back to here, I showed you earlier, this full data, this is index axis, so it has 7 bands. This is axis 0, this is 1 and 2. So if you're calculating axis across this one, that means it's collapsing 7 bands into a single one. And then, so in that way, you have an imagery that's just one single band as the outcome. So let me show you here. If you scroll down to using this one, so take a look at this. So right now, if you're calculating this way, getting the maximum, so I will say maybe max image equal to this one. And you can take a look at the side, the shape, max image dot shape. Does it make sense? So right now, you're getting this imagery is the same size of the original one. But what this one is really doing is calculating the maximum value for every pixel. So every pixel is going to have a maximum value across those 7 bands, right? So once you have this, you can also do the plotting. So similar to the one that we calculated for the NDVI, we can do the same thing. So I'm going to show you in here. And so all we need to do is just change this one to the max image. Just plug in this one into the plt.imshow. And then you can have -1, I think the minimum value we can change to 0 because that's the original value. So this is the reflectance. So it's going to be from 0 to 1 and take a look. So this will be the maximum value calculated for every pixel across 7 bands at each individual location rather than summing up all together. So in that way, you will see here, right, you have 7 spectral bands. So you can use this one to calculate what's the highest reflectance of every location across the 7 bands. Of course, the color doesn't look very good because most of the value range from 0 maybe to 0.5. You don't really see the green color in here because the value are pretty low. So what you can do here, I can change this one maybe to 0.5. Right? So now it looks a little bit better. You can also use the gray scale color if you want to, but as you can see, you can calculate. This is similar to, I think, in ArcGIS. It's called raster statistics. So you can input an image and they can calculate all of them for every location. And this will be useful in the case, some use cases like this. I'm going to give you a temperature data for the entire US. And I'm going to give you the data for every month. Every month you get one imagery for the entire US. And I ask you to calculate what's the maximum temperature for every location for last year. Then you can use this one. Make sense? Because every month you're going to have 12 months, right? So you have this imagery, you have 12 spectral, 12 bands. And if I ask you to calculate the temperature, highest temperature for every location, then you can use NumPy.max. So whatever, how many bands you have, and then you go axis 0, then you're going to calculate the maximum pixel temperature. So for example, in Knoxville, the highest temperature last year, maybe let's say 95 degree Fahrenheit, for example. And for Nashville, it's another one because it's different location. But you can also use just the whole data.max. Then you will calculate, okay, what's the maximum elevation, maximum temperature for the entire US last year. In that way, the location doesn't matter. You're going to sum them all up together. You're just going to get one number. Does it make sense? Right, so it depends on what you want. You just want a single number or you want a number for every location. Then you need to use it differently, right? So right now we are using it for every location. You need to use this one. If you use the other way, I'm going to show you one more time, full data.max. This one will give you one number. So imagine like the highest temperature or the highest elevation or the highest income or the highest soil moisture, whatever, right? You're going to get one number. If you want every number, a number for every location, then you use this way and then you need to provide the axis. So the axis, like if the band is at the beginning, the axis will be 0. If the band is at the end, then the axis will be 2. Okay, 0, 1, 2. How many rows, how many columns? So this is how you can calculate the normalized difference vegetation index. And at the end of the exercise here, also related assignment, I ask you to calculate the normalized difference vegetation index. And so you should be able to adapt this example. So right, the water index is green minus near infrared divided by green plus near infrared, right? So how should we do it? If we come back to this example here, so look at this here, look at this equation, right? So it basically is just the reverse. So what you can do here, let me show you. I can just do it simply, maybe create a new code block, and just to show you how we're going to do it. I probably should not tell you, so explore yourself. But so let's try see if it works, right? So it's green band. We already have the green band that we calculate from above. Green band minus near infrared band, and then the green band. Oops. Green band plus the near infrared band, right? And so this would be NDWI, for example. And then we can do the same thing, NDWI, right? The value will also range from -1 to 1. Similarly, NDWI, and that's it. I can change the color map to blues because there's a more common color map used for mapping waters, right? And after that, just run it. Let's see what happens. Oops. Blue is not supported. Oh, blues. Blues. Oh, okay. There's a typo. Uppercase. So you need to be careful. Lowercase. Blues. Take a look. So see this one here, right? So this is a normalized difference water index. You see here, this one is a reservoir. The values are pretty high, so they're close to 1. And that's why you can kind of see the water from here. And later on, you can also use NumPy to extract, for example, threshold greater than 0.5, then it is water. Otherwise, it's non-water. Anyway, you can export it later. So this is how you can do some simple raster calculation to get the result. So once you calculate this one, like how to actually export the result. So similar to the raster calculator in desktop GIS, you need to save the result. So in Raster.io, you need to be very explicit about saving the data and how many rows, how many columns, how many bands. So I'm going to show you this example here, how to actually save the result. So again, we're going to open the original data. So the raster path, again, we are pointing to the HTTP URL. So this is the metadata, basically the profile of the original data. And look at this one, GeoTIFF, data type, no data, negative INF, width and height, right? This is width, basically this column. Height is how many rows, right? Width and height. And count, GIS. So the only thing here you need to be careful is the count. So imagine your original imagery has 7 bands. Now we are calculating the NDVI. So how many bands are left? How many bands in the new imagery for the NDVI? Or the NDWI? Just 1, right? So you're getting from 7 bands to 1. And everything else pretty much the same except this one. The count is different. Basically, your outcome is different. But basically, when you are saving the data, you need to provide this kind of information. So why we're opening this one again is to show you these are the metadata of the original imagery. And it was 7 bands. Everything else should be the same, except right now we only have 1 band. So what we need to do here, if you look at this one, profile.update, and the date type, we are changing to floating 32. Actually, we don't really need to do it here because it's already the floating point is 32. And also the compress, the previous one is using the deflate. So you don't really need to change it if you don't want to. So the simplest one would be like this. I'm going to remove this one. and also remove the other one. So the only thing that you need to change, because this is a dictionary, so a dictionary can be utilized using the update function and then provide, okay, so right now the NDVI image we're going to save only has one band. So that's why we change the count to 1. If you run this one, you see everything else remains the same, but the count right now has been changed to 1. So this is what you need, because when you are saving the imagery to your computer, when you calculate the NDVI, it's just a NumPy array. There's no georeference information. So in order to convert from NumPy to georeference, then we need to provide this information. So what image format you're going to use, how many rows, how many columns, how many bands, what's the coordinate system, what's the GIS transform. So everything here you need to specify. And this is quite challenging for beginners. Like, why do I need to go through so many steps? Because you're getting a bunch of numbers and you want to generate geospatial data. You need to put them in, like, where's the location, how do we correlate this one to the locations on Earth. And after you get the profile, and this is what you need, these core blocks. So specify what's the file name you're going to use, and then we use Raster.io to open. So this file doesn't exist yet, so that's why we need to use the W mode. The W means write. And look at this one, profile. So you have 2 stars here. 2 star means you're going to unwrap the dictionary, and then you're going to fill in all the information inside here, and then open this file and then use the dst.write. So the NDWI right now we have this matrix, and you're going to save it as the first band of this output raster. And then if you run it, it's going to save the file, and it's going to show you, okay, the file has been saved successfully. So now if you go to your folder, you should find this ndvi.tif. So that means we calculate the NDVI, we also save the result to the computer. And so if you want, you can open this one, take a look at the file, the book, Geospatial. It'll be this one. It looks pretty dark, but I can clearly see the vegetation, right? A little bit brighter. This is where the vegetation value, the NDVI value, is a little bit higher. And you can verify it. For example, I can open QGIS. You can check the file, and you will notice if you are not specifying those parameters correctly, the file will not overlay on top of the base map. So right now, if I open this one, and then I open the map in here, so I'm gonna drag this one. You see, it's being overlaid properly on the map. So if you don't specify, so let me show you one more time here. I can save this one again, but if you don't specify this one, or if somehow this one is wrong, you may not be able to save it. So if I remove this one and then save this one maybe to NDVI2, it may not allow you. So you're going to show you, okay, integer width and height are required. That means it's a NumPy array, and when you're trying to save it, you need to explicitly specify how many rows and how many columns. And so what we can do here, I can even come here, comma, I can specify, okay, width equal to 2485, and then height equal to 2563. Okay. I'm doing here, but it's not recommended. Okay, I'm just going to show you the problem of this method. If you're trying to specify this one, and clearly it still doesn't have the georeference information. So let me see if I can save it. It still doesn't allow you. Okay, integer count is required. So that means we're missing one more. So I'm going to say count equal to 1. All right, a valid data type is required. Let's see, you start noticing how annoying it is. You need to provide all of them. So that's why earlier we used the star profile. That means it's going to unwrap dictionary and then change it to the way just like this. So I'm going to see the, for example, D type equal to float 32. All right, looks like it's successful. But You notice here no georeferencing, right? There's a warning at the end here, no georeferencing. So this is the second one that I just saved, and let me open this file and see what happened. You see, does it come up? It's not here. Where is it? Oh, it's somewhere in the ocean. You see? Why? Why is like in here? It's not supposed to be here. It is supposed to be overlapping. The reason for that is there's no georeference information. There's just row and column. So without it, it will not align with the map. I think this is very common. So I think if you ever use GIS, sometimes you will encounter issue like this. You open the data imagery or open the vector data, and it's just somewhere in the middle of the ocean because it's going to be the center 0 and 0, starting with the latitude, longitude 0 degree, and then going to go across that. And the number just super wrong, because if you go to the bottom here, it's how many rows and how many columns. So in this location here is roughly starting from, if you see here the coordinate, right, at the bottom here shows you that how many rows and how many columns. It's totally wrong. So that's why here is 0, 0, the latitude 0 and longitude 0, and it's not correct. Again, this is just something that you need to pay attention. So if you're saving the data, you need to make sure that the best way to do that is, okay, I'm opening a raster data, that one, everything is perfect, looks correct, georeferencing, and you're doing some manipulation. At the end, you generate some result, but you need to save it. So it's better to use all the original source information, all the metadata from the original image, and then you only update how many bands, because the width and height, the site is still the same. And the georeference is still the same. Everything is the same, except you might only end up with just 1 band or 3 band or 2 band. Then you use this way. But you do need to update the profile. So that's why we're using this one. So the easiest way, again, you'll be like this. Star profile. So what this one is doing is basically is essential equal to typing width equal to 2485, height equal to 2563, comma, CI equal to comma, blah, blah. So at the end, you have everything is being saved properly. So for example, NDVI 3, and run it. Now it should be correct. There's no warning. So everything is as expected, right? I can drag this one and zoom to here. So now it aligns perfectly on the map. Questions? Similarly, you can, let me show you. For example, so earlier we have 3 bands. Actually, we have this one here, RGB. So look at this one, right? You can even also save multispectral bands. So for this one, let's say you have an imagery, landscape have 7 bands. You extract the RGB, near infrared and red band and green band. How do we save this one, for example? How do we save this imagery to our computer? Basically, extract only 3 bands out of the 7. So earlier we calculated the vegetation, we only have 1 band, but right now we have 3 bands. And so the variable name here is called RGB. How do we save this one? What things we need to update? So how many bands in there? In the RGB image? How many? 3, right? Yeah. So what do we need to update? In here, right? Count equal to 3. Should be pretty simple. Everything else remains the same, right? There's no change to anything, the georeference. So what you need to do here right now, I'm just going to simply copy this one. Copy this code block. So use this as an example. So right now this should be okay, RGB.tif or whatever name that you like. But the only difference in here is right now we are writing, let me show you here, because you're only writing 1 band. But in this case, we actually have 3 bands. So we are just going to write all of them all together. So what you need to do here, just change the NDVI to RGB. And I think that's it. So let's see if it works. Oops. Shape consistent. RGB is considered given index 3. Do we need to have a comma inside? Or you can do it this way. So if it doesn't work, you can write it one by one. So use a for loop, for example. I will say, for example, for I in range 1 to 4, and then just like this one, ts write. So read, because we have 3 bands. So each time we're going to write one band and write the index into this one. So let's see, oops. Our data set is closed. Oh no, the RGB UB RGB. Interesting. So UB, let me look at the shape. RGB dot shape. Okay, so UB, each time UB the index, so comma, comma. I know this is a little bit annoying, but sometimes you just have to. Okay, tuple indices must be, or not the shape, it's the original one. Okay, so this is the original. So how basically getting the band 1, band 2, band 3, and then we save it. So we can do it like this way here. Colon, comma, colon, and then I. Oh no, I minus 1, sorry. And okay, so now it works. And let me open see if it's real. Nice, you see? So now we're actually saving the 3 bands into the imagery. So if you go look at this, right, rather than 7 bands, right now we have 3 bands, and it aligns perfectly on the original, on the base map. So what we're doing is extract 3 bands. Again, this might be a little bit annoying. It's I think you can just use dot write, but it doesn't work in here. If it doesn't work, you can always like, okay, getting the first band, and this index will be 1, right? So writing the first band into the imagery, and then we're going to get the second band. So the NumPy array indexing starts from 0, but for the Raster, the index starts from 1. So that's why you see the differences in here. So we are getting one band right into the imagery, the first band, get the second band right into the second band, get the third band right into the third band. So, but you do need to pay attention to the profile. Otherwise, your imagery will not overlay perfectly on the result. Questions? Okay, so next one, clipping the raster. This is also very common. So sometimes you have a large imagery, you only want a small piece. So I'm going to reopen this file again, the same file that we've been using, the Landsat data, and then you can look into the data. So this one here, just like what I showed you earlier, the strip is 7 bands. How many rows? How many columns? Right. So this will be the height. This will be the width. I think I got confused. So maybe data.shape or src. Let's see src.meta. So the height is basically how many rows. It's like height is rows 2563 rows, and then 2485 columns. Then because this is a shape of 3-dimensional, so we can do the indexing. So look at this one here. If you use just the column, that means you're going to get all the 7 bands. But we also have the other column. This is how many rows, how many columns, right? So what this one is showing here, from row 900 to 1400, and from column 700 to 1200. So if you don't understand it, you can go back to this imagery here. Look at the original one, right? So look at this one, right? In total, we have 2500 rows and 2400 columns. So if you're trying to do, for example, from row 900, you'll be like this. Somewhere in here, 900 to 1400, you'll be somewhere here, right? And so what this one is doing is giving you a Landsat imagery, and this covers Las Vegas. I just want the area surrounding Las Vegas. Make sense? So similar to, let me show you the desktop GIS in here. I just want this area, right? So if you want the area, then you can, there are two ways you can do the subtraction, because you already know how many rows, how many columns this imagery has. And upper left corner here is the index 0, right? So row 0, row 500, row 1000, right? So if you, for the Las Vegas, it's somewhere here, upper left corner. So it'll be somewhere in here, for example, around row 900. Make sense? And then to the bottom here, you'll be roughly row maybe 1400 here. So that means right now we are made two horizontal lines. And also in terms of column, right, vertical. So look at what's this. Somewhere in here, maybe 500, maybe 700, to another somewhere here, maybe 1100, somewhere like this. So this is why we put these two numbers when you're doing the clipping. Make sense? How many rows, how many columns? So you just use the column. So in this way, we are extracting just a subset. And after that, you can do the stacking again and show the imagery. So right now, the shape is 500 rows, 500 columns, and 3 bands. Then we display it. Look at this. So now we're basically subsetting the entire imagery to this one. We're using desktop GIS. You can use the extract by mask, for example, ArcGIS or QGIS. And then you can just do a clipping of the imagery. So if I'm using QGIS, for example, you'll be like this. We open this imagery and then go to raster, then go to maybe extraction, extract by extend, extract by mask. I can do extract by extend, right? And then from here, you can say clip extend. You can provide the bounding box, or I can simply here, okay, calculate or use the current canvas or draw on the map canvas. So it's similar to this one, right? And then I'm going to draw, for example, I want this area somewhere here, and then just one. Now you have this imagery, extract to this one. So using desktop, you can use these tools, but using programming, you need to know exactly where do I want to clip, because they cannot do it interactively. So you need to figure out, okay, where's the starting row and the ending row you want to extract, where's the starting column and the ending column, and they can specify the number, right? So in this case, we right now have 500 rows and 500 columns, and we get these 3 bands. And once you have this, you can save the result. And this is when it becomes a little bit tricky, because when you save the result, when you do the clipping, the row and column number changes. Basically, the width and height changes. If that changes, then the CRH transform also changes, because the CRH transform usually is tied to the upper left corner pixel. And now the upper left corner pixel is no longer the same thing. So I'm going to show you one more time here, right? src.meta. Or the profile, sorry, not meta, dot profile. So this is the original data. So when we are trying to save the result right now, oh no, this is RGB, whatever. The data, so the data here, look at this one, sorry. Data.profile, not the original one, because you only get the, yes, it's SRC. It's not right. SRC.profile. So again, I want you to look at this one. So the width and height, after you do the clipping, these two numbers need to be updated. Also, the count also need to be updated, because we only have 3 bands. We only extract 3 bands. And the other thing need to be updated is this one, the transform, F5 transformation, because this one is tied to the original imagery in the upper left corner pixel. But right now, you're only doing the subset. And this is what this complicated source code here is doing. If you're using desktop, you don't have to worry about all this. If you're doing programming, you do have to think about, after you do the clipping, where's the location, where's the latitude and longitude of the upper left corner of the clipping imagery. And so we're using this one here, the column, starting column, the ending column, the width and the height, basically the subset. And then you're going to get that window, and then the window passing to the bounding box. At the end, this is a new transform. So what we're trying to figure out is how do we update the GIS transform? Because the imagery size has changed. The upper left corner, you need to figure out the location. So if you run this one, and you can print out the new transform. Look at this. Right? So it's different from the original one. It's like src dot transform. Do you notice the differences? So this is the original imagery, upper left corner. Right now, this is the subset of the imagery. So the resolution still remains the same. Everything remains the same except this one. You update to this one, and this one update to this one. Why? Because the upper left corner location has changed. So this is using the GIS 3857, so the coordinate system. So anyway, when you are saving image to geospatial data, you need to tell it how many rows and how many columns of your NumPy array. You need to tell it what's the spatial resolution. You also need to tell it what's your coordinate system, what's the upper left corner pixel. Without that, your image will be messed up. You won't be able to overlay on top of the map. So this is one way you can do it. And after that, look at this. With open, and so this is Las Vegas. We're going to use W. And look at this. Right now, we are specifying this number, these parameters explicitly. But you can also use the profile and then use the profile to update the width and height and also the GIS transform. It should work as well. But if we're using this way, take a look at it. We open the file and then we write this sub block. And yeah, just use the dot right. Now we have this, all the bands, all the spectral bands extracted. So take a look. And so this is the, where's the Las Vegas? Why is it not showing up? Yeah, it should be here. Okay, here, it's here. So let me open it and see if we overlay on top of the map. Okay, pretty nice. It's here. So let me, is getting it correctly. So the GIS transform, again, the GIS transform is tied to this pixel. Tied to this pixel, this one, the upper left corner. So this is the one that controls where you put the map, and then it's going to scale out automatically to row and column. So without this one being placed correctly, there's no origin. The origin will be in the ocean. Make sense? So if I tweak this without this GIS transform, you can still save the file, but it's not going to be correct. So I can change it to maybe to Las Vegas too. You just tell you, okay, no geo reference. And then, so if you open this one up, Las Vegas too, and zoom to it, I'm sure it's going to be in the ocean. 0 degree latitude, 0 degree longitude, because that's the start by default is the origin of all the imagery if you don't specify the leg long. So this is how you can clip the imagery, specify the row and column, and then you can do that. You can also clip with vector data. So for this one, we're clipping with the vector data. So you can provide, for example, this one is using Fiona, and we use GeoPandas to read the file. So once you have the bounding box, you can plot them all together. For example, we have covered this one in the previous example. Given imagery, I can plot a vector data on top of that. But for example, if you want to use this bounding box to clip the imagery, you can do that as well. So we're going to, you need to use this so-called Fiona to open the file, and then you can get the geometry. So basically, we can use the geometry to clip the imagery. It's not very straightforward. Doing all the raster manipulation in Raster.io is a little bit tricky, but we use the GeoPandas to show you how to do the plotting. But we also need to use this Fiona package to open the file and then give you all the geometry. So if you want, I can show you what this looks like. The shape is actually a list, and inside the list, you can sort it, right? And then you can look at the basically just the coordinates. So this is basically the input format for Raster.io. And after that, we're going to use this function. So again, this one, the mask. So Raster.io has the mask, and then mask.mask, and then give me an original imagery, give me the geometry, and then I'm doing the cropping. So this is a little bit better because we're using the a vector data rather than you have to specify the row and column number. So for example, I can give you an imagery covering Knoxville. I can also give you a vector data covering Knoxville. Then you can use this way. You can open the vector data using this Fiona, get the geometry, and then you can call this function. Then you can do the clipping. So it's the same thing. So right now we have the clipping imagery. For example, Las Vegas clip. And you can drag it here. You see, it's the same thing. So we can use the vector data. So in that way, you don't need to figure out, okay, what's the starting row and column number for Las Vegas? Where's the ending one? It's a little bit annoying. If you have existing polygon, you can just pass it directly. So just use this example to do that. And similarly, right now we're using the width and height has changed. Also the out transform. So the out transform is coming from here. So Raster.io can calculate it automatically. Again, if you want, you can print this one out, out transform. So you will see here, this also the number has been updated. Questions? I know it's a little bit challenging for beginners. Like, why do we need to do so many things? Because you need to take care of every aspect yourself. Later on, when we introduce leaf map, you don't need to worry all that. It's just one line of code. Give me an imagery and then give me a vector, then you will do the rest. But this is like doing the low level things. And it's actually when you start doing programming, learning programming, it's better to understand what's working under the hood rather than just clicking the button, right? You can always use ArcGIS, QGIS, and then do the clipping, doing the under the hood is actually executing code like this, but it's doing it for you. So if you don't understand that, you just assume that everything is just simple. It's not like simple. Yes. Yeah, basically it's a mask function under the mask module. So Raster.io has the raster dot mask. So you go to the beginning, I think somewhere here, import the I think it's in maybe this section. Clipping, no, this one. Maybe at the beginning. Control F, Raster.io dot mask. Go down. So basically in here, Raster.io dot mask. So it's a sub module of the Raster.io class. And under this module, there's a mask function. So if you go here, create a new block, it's kind of like Raster.io dot plot dot show, right? It's kind of like you can also import Raster.io dot mask as like another name, but this looks like the hierarchy because Raster.io has this mask. So Raster.io dot mask, and then if you type dot again, it has a bunch of functions under here, and there's pretty much just one mask and then NumPy or other geometry mask. If you really want to look into that, you can go to, for example, Raster.io GitHub, and you can go to the GitHub repository, and you can go into the, I think it's under Raster.io. So this is the whole package. Inside the package, there are multiple modules. So there's a module called mask. And inside this module, there's a function called mask. And that's why it's like Raster.io.mask is because it's hiding behind this module. But if you find it confusing, you can do it like this. Import Raster.io.mask as maybe RM, something like that. And then you can use rm.mask, so it will be less confusing. You can give a so-called alias of the name. Anyway, good question, good observation. So last example is about doing the reprojection. This one is even more complicated. Like so many lines of code, it's hard to understand. So in desktop.js, you'll be like this. So you're having this imagery, right? You can right click, you can export, and you can save as. And so usually in here, right, this is where you specify the georeference information, the coordinate or the projection. You can open this one. Similarly in ArcGIS, you can do the same thing. I can change, select whatever you want, or I can search this one, for example, 50, 70. And you can change it to whatever you like, and then just save the name, and then you can get it. But in programming, there are many lines of code you need to write. Open the file, and then do the code default transformation, get the new out transformation, and then inside here, when you save the file, it needs to specify this new transformation. So this is the most annoying thing when you are dealing with raster data. Again, in leaf map, there's one line of code, do project, and then give me the input, the output, but I'm showing you the underlying code here, so they understand like when you're doing a QGIS, behind the scene is also doing something very much similar, but it's just taking care of things for you, so that you don't have to worry about it. But you do need to understand like why it is doing this, because when you're doing the transformation, the rows and column number might change, and also the upper left corner is going to change because the projection is different. The upper left corner, that origin has also changed, so that transformation need to be calculated, and this function is to help you calculate it automatically, so that you don't have to. Once you get this transformation, then you need to pass this one to when you save the file, the profile, so that you will be saved correctly with the correct number and row and column. All right, so this is how you can do that. And the last example is like, sometimes you might need to create raster from scratch. We don't have time to go through in detail, but I'm going to show you, for example, this is, you're creating a bunch of NumPy array, and then we can use Matplotlib to plot it. So this one is using the contour. Looks pretty nice. So you can actually generate synthetic data using this. So this is just showing you the imagery, like how many pixels. You can think about, for example, this is a DEM, so you can generate some DEM, and Matplotlib can allow you to create 3D. So this looks even better, and kind of like mountains, valleys, holes, something like that. But it's just a two-dimensional array pixel, and in this way you can represent it in this in 3D. But again, you can look at this X, Y, Z, right? So it basically they all have the basically location, how many rows, how many columns, and G is just the value. So if you want, you can type G.shape uppercase. You can see it is 180 rows, 240 columns, right? Kind of like in here. This is how you create basically the linear sequencing. How many number of points, how many rows, how many columns, and oh no, how many X is how many columns, Y is how many rows. This is always confusing. Different software use row and column, use X and Y, so sometimes you have to be careful. Anyway, but the last example is if you want to do that in even 3D. For example, here, this is using Plotly, and this one is nice because you can rotate, so you can see what's in there. So basically, for all the raster data, you can plot using 3D if you want to. Of course, the code looks a little bit complicated, but you can digest it later. We don't use it a whole lot because later on when we cover leaf map, we're going to use leaf map to do all the visualization. You don't need to write this many lines of code. So usually it's just one line of code. You can do that automatically. But I want to provide some example, then you can customize it. So you can use this to plot any, for example, raster data, DEM, something like that. And after that, you can save this one to your computer. Again, the most tricky thing is always the transform. So you need to figure out where's the upper left corner transform, so that you can write this one to your computer. Okay, so that's all for this lecture. Again, take some time to digest, play with it, do some raster manipulation, and then get familiar with that. If you cannot really understand everything, that's perfectly fine. You can ask ChatGPT to help you. But we not use this a whole lot. We introduce easier way to handle this later using other packages. But it's important to understand under the hood when you previously used desktop GIS, how they're actually doing the stuff. Is executing something like this very similarly. So once you understand the basics, it's much easier later on when you use some other easier way or interface to do that. Okay, so that's all for